Hello and welcome back to episode number 9 already of hacking our Raspberry Pi Pico emulator. And I can see on the chat already that we have here Tony from Finland. So hey Tony, I think you are the guy who created the Python assembler or disassembler for the RP2040. Anyway, let me share my screen and start with some good news. So last week, I think we made, in my opinion, pretty amazing progress with getting GDB to talk to the emulator. And we left behind 3 instructions that we knew that we needed to implement, but I wanted to first focus on getting the GDB to work. And then at the end of the episode, I asked the folks here if you could, come up with a pull request. And some nice guy named Brian actually did that. So he sent me a pull request which implements all these 3 instructions. So it's his first time working with TypeScript, so we'll have a look in a moment. I'm pretty excited that it actually worked, and I see Steve here on the chat as well. So hi, Steve. So let's take a quick look at what it did, and hopefully we can merge it and then continue with the GDB fun and see where we were last week. So let's see. So first of all, I can see he added a few tests. That's great. And yeah, that's the implementation of the instructions. Let's make the font a bit larger. And let's take a quick look at the assembler and see if it makes sense. So let's put it side by side with, what was that? Yeah, that's our code, with the commit message that reminds us what we needed to do. So let's see. ASRS R3, R2, 31 is the value is good. And then EORS R1, R3, and yeah, same value. And SXTB R2, B2, 52. All right. One thing I would probably improve here is check SXTB with a different pair of registers, because using the same register, we might swap them in the implementation, and we miss that when we in this test case. But anyway, let's take a quick look at the implementation of SXTB and see if it looks correct, of the encoding of SXTB. Where was that? Here we go. SXTB. So yeah, so in all of our opcodes, the order is reversed, so it's always RD/RM in the assembly command, and then and hi GCM in the chat, and then here the order is reversed, and it seems to be following the same pattern. So I guess it's good. I mean, yeah, it seems good. And there are tests, so I guess we can say that the opcodes are fine and the code seems nicely formatted, like we would write, like I would write it. So I think that's great. Now let's take a quick look at the test cases. So ASRS, I think it's ASRS is like arithmetic shift right? Where do we have this data sheet? ASRS peripherals, no, not that one, this one, and that was instructions. I'm already getting really good at navigating this data sheet. So ASR, arithmetic shift right. Yep. All right. So By the way, just out of pure interest, how do you find out about the weekly streams? Like, do you get it from YouTube, or I have this small mailing list where I'm sending an email every week, or through Twitter? I just want to know what's more effective and what not. So while I'm talking, please, if you can, let me know in the chat how do I don't know if you have it on your calendar. So how do you find out about these weekly streams, about the next stream and everything? So please do this while I'm keeping I keep looking at this implementation. So we have the opcode R3, R2, shift by 31. And then since it's an arithmetic shift, we expect it to copy this bit all the way. It looks legit. And now this is negative. This is not 0. And how does this work with carry? Does it have any carry? Where is the carry flag? Carry is the result of the shift, and that's ASR. What does shifting with ASR do? Shift C. Shift C, so ASRC. There isn't a carry in here. So carry out, I guess it's the last bit that we dropped, and in this case, I think 0 would be the right, like it should be false. The bell alert, like in YouTube. Okay, cool. And hi Nekati. So thanks for that. So because I just want to know what's the effective way. So if anybody is watching it and you want to get notifications about future streams, just seems like everybody is using the bell on YouTube, and that works. So it's perfect. All right. So I think this one is good. The test case seems good. Let's take a look at EOR, which is just exclusive ORs or XOR. Let's see. F0, 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 so F and 0, F, 0 and 8, all right, and F and F0, 0 and F. Okay, I think it's probably good. I mean, I could make my life easier just by checking it instead of manually using the machine. So no, we want it to be unsigned as hexadecimal. Yeah, the test case looks good. We tested the test case, and that's negative. The MSB is set, and that's definitely not 0. And 2 tests for SXTB, and all right, with sign bit 1. Okay, cool. You did walk the extra mile to check it with. I think SX is probably sign extend whatever, something byte, right? Let's see, SXTB, where are you? Sign extend byte extracts 8-bit value from a register, signed extend to 30, and right. Okay, cool. So it's just a sign extend. So yeah, so if we have this value, it extracted just the lowest byte, right? It only extracts 8-bit value from the register. So probably rotation is 0, yeah. So yeah, it just extracts it and sign extend it. So we extracted it, sign extended it, and yeah, seems legit. And there aren't any flags to worry about. Cool. So the tests look good, and this looks good. I guess. I hope he copied it from somewhere else, so I probably don't have to test it too much. Yep, we already did this in LSRS, and this is ASRS. Probably the same logic, so I would say this should be good. EORS, I guess there isn't any carry to worry about. Let's see, EORS. Carry is probably unchanged, right? Yeah, LSL 0, so it means carry just copied. Perfect. So I think this is good. And SXTB, just taking this value. That's an interesting way to sign extend. So basically taking this value, shifting it to the left by 24 bits. So we have the 8 bits, the 8 least significant bits become the 8 most significant bits. And then we shift it right all the way back, but that's like an arithmetic shift. So if the leftmost bit is 1, then it will copy it all the way. So yeah, I like that. That's clever. I wouldn't have thought to do it this way. I think we actually already have like a method that does this sign extend, but yeah, so he could have used that method, but that's a pretty clever way to do it. I like that. Anyway, the pull request looks good. I mean, I will merge it. Normally, I would probably have left a comment here that says we have a method that does that. So just use that method, and then you can change the method to use this clever trick if you want. But this is like I can do it. It's a small thing. I can do it myself, and I really want to start using those instructions. One more note. Usually, I think you have noticed that, but I try to follow the conventional commits format where you have like this verb. In this case, it's fit for a feature, or I think we only have, we had it also fix if we fix some bug, and then optional parentheses with the component that we changed. So either like the core class, the RP2040, or in this case the GDB server, and then colon and a short description of the change. And in this case he didn't follow this this convention. So again, normally I would probably have requested those changes, but I'm I wanted to do the review online here, so you can see the process as well. You can be part of it. So in this case, I'm just going to merge, and there are like a few options. I can just merge with a new merge commit, but in this case, I'm going to do this, which makes just puts the commits, the commit that he had on top of my commit. And the advantage to that is that it lets me rewrite the, or it should let me rewrite. Usually it does. Maybe when I click on it, it does. Yeah, it lets me rewrite the commit message. So I can make it follow the format that we use, like the conventional commit format. And I think, yeah, we can just say add or implement those instructions. And then I'm basically fixing one of the issues this way. I'm squashing and merging, and voila, party. Thank you so much, Brian. We now have those instructions. Let me pull them locally so we have them. And let's run the tests, because I guess Brian did run the tests, but I want to see it passing in my eyes. Eventually, we can probably have some kind of CI that automatically runs the tests, or even a commit hook that wouldn't let you commit without running the tests. But yeah, I can see that all 122 tests have passed. And if I go to the spec file, I should see the new tests. And finally, Yeah, I could use the sign extend 8. Yeah, let's do this instead of like that trick is clever, but I mean, we can probably adopt it for the sign extend 8, but we already have a method that does that, so we don't need to reinvent the wheel. Interesting, but I think our sign extend might have been wrong all the time. So yeah, I think we should not only when like it's a negative number, we should definitely it's wrong. So it's a good thing that I actually did this change, because now thanks to his test case I figured out that our sign extend is wrong. So basically, instead of this, I should have probably set all the bits to ones, except for the ones that I already have. So we can do it like that, or we don't even need this bitwise AND, because we are just setting the bits to 1. So we can do it like this, and now it should be green, I hope, with this small fix. Not yet. Why is that? SXTB and LDRSB. So if this bit is set, then set all the other bit. It looks legit to me. Let's see what's the thing. What's yeah, okay, let's focus on this test and then go to the implementation. All right, and then value to string 16. Okay, it's getting the correct value, and then this should be false, I guess, because obviously this bit isn't set. Yep, so it should just return the value as is. Oh, yeah. Right. In this case, we actually want just to return the low byte. So yeah, so that's another way to sign extend. Now it's almost green. We probably have a bug in one of the other tests, because this was buggy. We didn't catch that in the tests. So let's check out the test. So LDRSB, probably S is for sign extend, and we are doing essentially the same. So yeah, so it's loading this value into this, and since this is negative, it should be, yeah, it should be, we should have extended it properly. So yeah, but at least I'm happy that I'm not the only one that didn't pay attention to this mistake in sign extend. And now when I'm looking at it, I see that we have the same problem with sign extend 16, so we'll fix it as well. And you know what, I actually liked that was Brian, right? Brian's approach more than the wizardry I'm doing here. So basically just value shifted by 24 and then shifted by 24, and it does the same, so it's shorter. And I think I don't think this is less readable than this. I think they are unreadable by normal human being in the same way. So here we just want to shift it 16, so we have only the 16 lower bytes, and then arithmetic shift them right. And then again, we probably have this other test case that should have yeah, should have done the right thing, but did the wrong thing. So great. Not only Brian helped us implement 3 instructions, but he also helped us find 2 bugs that would have probably hunted us someday in the distant future and tortured us for, I don't know if minutes or half an hour or I don't know how long. But anyway, thank you so much, Brian. That's a great job. I mean, first time working with TypeScript, and you did it really well. So thank you. And now let's commit that and RP2040 bug in sign extend 8 sign extend 16. Let's just take a quick look at the files before we commit. All right. Okay, so yeah, we changed this test case and this one because they were not testing the right thing, or they were not making the right assertions, and then we fixed those 2. And finally, we changed the code to use sign extend 8 instead of hard coding it here. And this is not really required as far as I can tell, because we are only working with 32 bits, so we don't really need to mask only the 8 lower bytes, because by shifting them all the way to the left, we are just getting rid of all the other bytes. So that's clever. All right, so let's fix, commit, and then push this. And I think we just broke a record. Like we are 20 minutes into the session and we already did our first commit. Okay, great. So yeah, let's see, where were we with the GDB thing? So this is the GDB server, and we have some uncommitted line. What's the thing here? Oh yeah, we left a comment which explains about a register we probably didn't know how to do. So let's start by doing that. So basically this G command, let's actually add some comment here, read registers, and this one is reading the memory. So it's a big context switch. So now we are switching to work on the GDB server. That's the part that we implemented last week, where GDB is talking to our emulator and is probably going to be able to debug the program that is running in the emulator. And you know what? Before diving into that, let's just get that to run. So I guess npm start to run the code, and it's printing a lot of stuff. So I probably want to, output, let's set it to the output file. So I won't have all this jump. There are a lot of breakpoints here. What is going on? So, oh yeah, I think we had a different entry point for the GDB server, right? So GDB, yep. So probably in package.json we can find it. Yep, yarn npm start GDB. npm run start GDB. Yes, thank you, npm. And last time. Okay, GDB server ready, listening on port, whatever. So it probably just runs the code for, it runs like 20,000 instructions, and then it launches GDB. So let's take a look at GDB. Let's start GDB. And last time we had to run this code inside WSL, Windows Subsystem for Linux, or whatever it's called. Because I couldn't connect from Windows to my PC, but now I figured out like the firewall settings, so I can connect from let's actually do it more manual so it's easier to see what we are doing here. So this is like me running in the WSL, and first of all I'm going to load the symbols for Blink. So that's blink.elf, or no, we are not running Blink here, we are running hello UART. Hello UART, I think it's UART, hello UART, hello underscore UART, and then we have the elf file, so GDB, and then no, I want the multi-arch GDB, so it's able GDB multi-arch, so it's able to talk to my simulator, which is ARM, and then file hello UART.elf, and now that we have the files we can connect. So target remote WinHost, that's my Windows PC, and the port is 333, and yeah, we can see they are connected, and we can see like they are talking to each other. That's so nice. And we can see where we are. Let's switch to the text UI. I don't know if we talked about that last time, but it allows me to view where I am in the code. And then I can do where to see also a stack dump. So I can see like the assertion that failed. And you know what? I try to disable the TY, but it did something really yeah, let's get back to the TY, and now I disabled it. No, so I will reset the terminal. I ran shell reset to just reset the terminal, so GDB won't get messed up. And now we can see like exactly the complete call stack of where we panicked. So I just want you, I don't know if we still have that output file. Yeah, just want you to compare this with the experience of just going through this code and manually figuring it out like we did up to now when we have GDB. So I think that's going to be a game changer for us. And we can already see like we are we are like we can even see like the arguments, like we are having like this IRQ is the number is 3, and this is like the entry, probably a method that handles this IRQ number 3. I don't really know what it does it, but I can see all like the arguments and everything. And actually the nice thing, if I do the same but from within, or you know what, maybe no, let's do it one step at a time. I'm running, I'm really excited about this, so my thoughts are running in all directions. But if we just run this in inside the terminal here, instead of like in a different terminal, where was that? UART, hello UART, yep. And then GDB multi-arch. Then we can already pre-execute the commands, because we know that we want to load hello UR.elf and then target remote WinHost 333. So now, yeah, I think it got confused. So let's just restart this thing and then reconnect GDB. Okay. So, interesting. Oh, I needed to use file and not load. That's why GDB gets confused, because it doesn't, probably it looks at the elf file to determine the architecture, and now it didn't see, like we didn't give it any file with the symbols, so it didn't know what architecture to expect. So it said truncated register 16. It probably tried to read the list of registers for like, yeah, a different architecture, probably like this X with x86-34. Anyway, now this should work, and yeah. And now if we type where, and we since we are inside the Visual Studio Code, it should recognize those file names, and if we click, we can just go directly to the file, which is like super convenient. So we can see like the entire context of where we were. Cool. So that's where we are at, like after last week. And what I want to do now, I want to let us interact with the code. So if we switch back to the SRC layout, we can see we are like in this line, and right now there is nothing much to do. Like we can inspect values and see what the current situation is, but we can't really see how it got into here, like other than looking at the current situation. We can't really step through the code. So what I'm going to do now, I'm going to start to see if we can implement that. So with the GDB server code, we will start at the very beginning instead of executing 20,000 instructions when we start it. So let's start it. So and let's reconnect GDB remote winost 333 focus CMD, so I can use the history. Yep, and now we can see that we are in the very beginning in at flash binary start, and hopefully at this point I would be able to tell it that I want to break, let's say, in this function. So I can set a breakpoint, but then and it tells me that I have let's disable the TY so we have a full view. So yeah, if I do info break, I can see that the breakpoint is there. But now if I try to run the code, you see it's not happy about that. It actually continues to run the code, or I don't know what it does. Like it doesn't do what it's supposed to do. Now I can't even, yep. It just kills the connection basically. And even if I wanted to step, I couldn't do that. So if I go to there is also an assembly view where, am I connected? Interesting. Yeah, it probably doesn't. Is it connected? I think I'm not, because where I am right now. Where am I? What happened? Yeah, let's just restart GDB. Okay, so yeah, now it seems more connected. So there is like this command that shows me the assembly view. So ideally, I would want to be able to step. So SI or stepi would step to the next instruction. But I see that this doesn't happen because we haven't implemented it yet. It just gets stuck. So let's do that. Let's start by implementing this single instruction, this instruction stepping, and we can see that it sends a few commands when we try to step. So let's take a look at them. So first of all, let's finish documenting what we have here. So we have here read memory, read registers, and Q is like query things, probably supported features, whether we are attached, and so on. And then let's reconnect GDB, disable the TUI for now, winhost 333. Yeah, we should probably reduce the amount of prints. And then I want to say set, first of all, yeah, we can see it stopped after this Q symbol, set debug remote 1. And then when we do step I, wow, it sends a lot of stuff when we are doing step I. And I guess one of the reasons is because we have set a breakpoint. You can see it's sending a bunch of M packets, probably reading some stuff in the memory. And I guess this is setting the breakpoint, and then they are trying to set a breakpoint in all sort of ways. So instead of like, yeah, I think we broke it again. Oops, I did it again. Let's restart that. So instead of doing it the hard way, let's just delete the breakpoint. There is no breakpoint. Okay, so maybe it's just stepping with a breakpoint. Interesting. Let's restart GDB again. There is no breakpoint. Okay. Set. I want to debug. Set debug remote 1 and then step I. Yeah, and it seems like it does try to do a lot of things when I'm stepping. I think the interesting command here is C, and if we go to the reference, or it's one of the, first of all, we can close that, we merge that happily. If we go to the reference of the GDB packets protocol and look for C, where are you C? Yeah, so C is just continue, which means run the program at this point. And then we also had, I think, Z, which is probably a breakpoint. So Z, yeah. So there is like software breakpoint and hardware breakpoint. But I think, if I remember correctly, when GDB can't put a breakpoint using those commands, it just uses a different command, which is the M command, which writes to the memory. So it basically tries to overwrite one of the instructions with a break instruction. And I think we already implemented break, so we can take advantage of this behavior. For that, we need to implement this M command, which is like just write memory, uppercase M. So let's start with that. So write memory. And then it takes address and length, colon, and XXX, which is just 2 like bytes represented as 2-digit hexadecimal number. And we can see an example here in the log. So basically, if we go to the where was the GDB? Yeah, if we go to the GDB, we can see that, or we can, yeah, this was the address we stopped at. And then I guess it's since we wanted to step one instruction, it probably set a breakpoint by writing data to, I don't know why it adds 4 bytes to the address. Maybe the first instruction was, let's restart GDB to understand what's going on here. Yeah, is it connected? Yeah. This install our PC. Yeah, so I don't know why did it try to overwrite that instruction to step instead of the next instruction. That's interesting, but let's try that again. Step I and see what it did again. So yeah, apparently even when what is an X packet? Anyway, even when you try to set a breakpoint with the Z instruction, it already did that with that address, with the address of the not the next instruction, the one after it. So I guess what it's doing, it's just like taking a look at the current, it's reading the current instruction from what it believes. Interesting. Yeah, I don't know why it does that. But yeah, you can see it's like reading the memory at the current location. So in this push LR location. And then it says that these are the bytes in the memory, and then it does that again. I'm not sure why it does everything twice. That's interesting. Then it reads the next 2 bytes after that, which is like this moves instruction. So it verifies when I disassemble. I'm not sure if it reads from the memory or from the L file but that I loaded, but now it just goes to the memory of the real device, or in this case the emulator, and verifies that the bytes in the memory are equal to what it thinks they are. And you see, like, it reads from this specific address where we are at right now 1, 2, 3, 4, 5 times, and then 2 more times from this address. It's not very efficient. And then it tries to set a breakpoint, but we reply with an empty packet, so it concludes that this is not supported. So it now reads again the bytes from this next location, in this case 4 bytes, and then I'm not sure what is the X packet, but it's not supported anyway, so it tries to just, replace those bytes with, probably this is the encoding of a break instruction, and then we don't support that, but it ignores that and continue, and then it tries to vCont, which is probably just resume the program, and we don't support that, so it just sends this C packet. So let's try to implement this uppercase M and see if stepping works. All right, so we have like those parameters, like so let's do it like that. Actually, we can probably, instead of doing this const params in every switch case, we can probably move it to the top. So and then we can do like the address and the length. Oh, did it also split it by comma? Yeah, so let's not do it, because I'm not sure that all the commands have this format with a comma. Yeah, let's just copy that for now. So yeah, we have address and lengths, but in this case we also want, oh, it doesn't like the fact that I'm using the same variables, because in JavaScript, I think also in C, all the cases live in the same scope. So it's a good practice to wrap them in a new block, like in those parentheses or curly braces where I declare variables. Let's also do it here, because I declare a variable. And then let's do it here as well. So yeah, so in this case, I would need a bit more parsing. So I would want to split by, we can split by a regular expression. So either comma or semicolon. And then we have the address, the lengths, and then we have const data. And yeah, it's actually the reverse of hex. Decode, the reverse of the encode hex buff that we had. We have an encode hex buff? Okay, decode hex buffer, and just decode the second parameter, and then let's decode hex buff. So code hex buff, and encoded is just string, and then we just go result is every pair of characters is 1 byte, so we can easily calculate the length. I is 0, I result length I plus, result I is encoded substring I2, and we have substr, which takes length, if I'm not mistaken. Yep, that's, I think we talked about that last time, when we have in JavaScript substring that takes start and end, and substr that takes start and length. All right. Oh, and we also need to convert it to an integer. So parse int with base 16. And I think we are good to go. We have this function that decodes the hexa buffer. And then all we need to do is just probably write it to the memory. So I data length I plus plus, and then we can say data at I RB2040 write unit 8, and we can probably optimize it. So like if we have like if the size is divisible by 4, such as in this case, write UN32, but at this point I just want to get it working, we can always optimize later. So others plus I, data I. Cool. Now why isn't it happy? Because we forgot to return the result. So it returned nothing, and nothing doesn't have a length. So thank you, TypeScript. And yeah, I think this is good. Let's see if we should reply. Yeah, we should say, okay, if we are successful, so return. Let's skip this comment though. So return GDB response. Okay, cool. So we can, we have this command as well. And now the next thing we want to have is like this continue command. So yeah, I will put it at the top because I think it's super important one. Case not in Hebrew, C. So continuing here is interesting because when we continue, we actually want to keep executing instructions, but we don't want to do that forever. Rather, we want to do that until a certain condition is met. So for that, we would need to support this kind of like breaking. So I will create a new method. Let's call it execute. That will just run the code instruction by instruction. And yeah, let's creating that method. And that method will need to know when to stop. Yeah, let's put it at the bottom after this monstrous execute instruction that we have. And basically it's while true, then this dot execute instruction. But doing that will just block the process because it will keep executing instructions forever. So in this case, do we have like a break instruction, or did we implement it? We haven't implemented a break, so maybe we'll output. Yeah. Yeah, I think those two pieces are actually that we see here in the log are actually this loop that does breaks. I think I vaguely remember that we did do at least the decoding for break, but I don't see that. Yeah, and the fact that break is actually a keyword in JavaScript doesn't really help, even though there are like only a few occurrences. So we can take a look here. Oh yeah, it's called BKPT. All right, so we just in this case we just print breakpoint, and so instead of doing that, we would let the user decide what to do when we get to a breakpoint. So let's declare a new property that the user can attach to. In this case, the user is the GDB server, debugging. So public on break, and by default, so it's a method that takes nothing and returns nothing, and by default it will just print a message and kill the process. Yeah, I think that's a good default behavior. No, I'm just kidding. In default, it will just stop the execution, and we'll get to how we stop the execution in a moment. But first of all, let's use this method, BKPT. So instead of Oh, there is like I think that's a reason this this value that we have here, where BKPT, no, BKPT. Yeah, so there is like this IMM8. Oh, actually, if we don't have a debug port, we should probably cause an hard fault exception, but we don't have exceptions yet. But yeah, 8-bit I ignored. Yeah, we can just like pass this value to the breakpoint, and then break it here to do hard fault exception in, maybe that should go also into the break, because yeah, in the default implementation raise, and let's call that code, and then we can say, so this syntax might be a bit confusing for those who are not very familiar with TypeScript. This is basically the type of the function. Yeah, I can probably omit it, and yeah, I think I will just omit it because TypeScript can already infer that this function takes code and doesn't return anything. So yeah, so now we have this function, and then I have this like execute, which runs while true, but I want it, I want the code to be able to eventually stop the execution. So in this case, I can do this with another variable. Let's call it running or stopped. How should we call it? Naming things is always so hard. Let's call it stopped. So it's false by default, and whenever you call execute, it sets it to false again. And while while we are not stopped, then execute instruction, and then I can say that by the default breakpoint handler will just this.stop equals stopped equals true. Actually, let's make this variable private, so people won't touch it, people like the users of the class. And let's make another method called stop that takes care of setting stopped. So if at some point we decide to rename it or to, you know, change the semantics of how stop works, we are no longer constrained by this external API. So the external API is just calling this stop method. I think it's also better explaining or a better API. Cool. So now in the GDB server, all we need to do is just to say this. So C will call execute, which will continue running instructions, and then whenever I get yeah. So whenever I get yeah, a connection, I will do this. So whenever socket dot, so no, RP2040 on break. So whenever we get a breakpoint, instead of using the default handler, first of all, we'll stop the execution. And then the next thing, we would need to tell GDB that we stopped, like that we are ready to accept further commands. And I think there is like a string that we can send to tell GDB that we are stopped. I think we should just send this the status code that tells GDB that we are stopped, but I'm not sure which status code. So first of all, socket.write. Okay, and now let's take a look at the documentation to see stop reply packet sounds good. Sounds like the way to go. So all these commands can receive any of the below as reply, except for question mark and vstop. This reply only return when the target halts. So S is like what we are setting. The program received signal number AA, but where are the signals? Is there like any documentation about the signal numbers? Maybe here, like the T is like S, but it's probably including information about multiple threads or something like that, which we still don't have. At some point we may have to worry about it, but not right now. Okay, is there like signal number information? Oh, it's defined in this header. Nice. So I actually have to Google that now and look at the header. Yeah, it's defined here probably. Okay, so yeah, so we can see like all those signal numbers that we can return, and specifically we currently have like this S05, which means trace breakpoint trap, which sounds pretty cool. There is also emulation trap. Nice. So yeah, so this is like this sounds like a good stop reason. So we'll just use that and see how it works with GDB. Okay, so let's try that. Let's go back to GDB. We added those two commands, M to write memory and C to continue executing code. And let's just restart GDB, and the code is already running. And let's see what happens. So we are connected, and let's do stepi. And oh, wait a second. Interesting. So yeah, it didn't stop in the next instruction. It actually continued running the code until the code had a BKPT. So I wonder if GDB is using some other way to tell us whether we should stop. And obviously it will be a little hard to see here because we have a lot of spam. So it worked in a way. We know that when we continue executing the code, it keeps executing, and when we have a breakpoint, it breaks. But something else didn't quite work. Either we didn't write the bytes to the memory, or we didn't like GDB does insert some opcode that we don't understand, and we have a lot of output here. So we can probably see what happens now. We write to Victor. Nice. I remember this Victor. Anyway, yeah, a lot of fancy stuff. Anyway, let's just retry it and see what GDB sends. So we can have a better understanding of what it tries to do. Set debug remote 1 stepi. Yeah, well, it does send a lot of stuff, but yeah, much less than what we have seen before. So so it sends this memory write, and it writes these 2 bytes, F001, F0E7, and then it resumes, and this is where we stopped. So first of all, let's try to understand what it writes here. F001. I think we have seen a way to decode opcodes. And this is actually 01F0 because this is Little Indian. Let's see. So that was the instruction set, and there was that table that I think it's something about the opcode. Yeah, so we said it's like 01F0, right? So the opcode would be 0 in this case, which means it's a shift. That doesn't make a lot of sense. Maybe it's a 32-bit instruction. Probably not, because they have like the first byte is high. So I'm not actually sure what GDB is trying to do here, why it is writing this this value here. I assumed it would write the opcode of break. Let's try to do something like that. Let's try to tell it to break at main, just for the sake of it. And yeah, we can see it read the memory address where main is. And let's try to continue. So GDB works like this. Whenever you step or continue, it actually it sends all the breakpoint at that point. So we can define a lot of breakpoints, but they will be created only when we continue or step, and they will be cleared when the program returns. So yeah, let's do continue, and we can see that. So this was the breakpoint where we wanted to put it, and we can see that it writes 2 bytes to this address 01DE. Interesting. So in this case, I think DE is probably the correct opcode. You know what? Let's just try to see how it works. Let's restart the program and try to set a but yeah, we wanted to break here. So yeah, so let's try to set a breakpoint, a proper one, and see if this works, because it seems to write something to the correct address. So let's break here, and then let's continue and see. No, it didn't stop there. So what I guess might happen is that we have a bug in the code that writes to the memory, or it's sending a different opcode. So info set remote, set debug remote 1, continue, and let's see what it writes there. So that's where we have the breakpoint, I guess. Yeah, D7C. So we are reading the memory, and this is, we are reading it twice for some reason. And then DE01, that's what we write to this memory to set the breakpoint. And let's see what's DE01. So DE01 to string 2. All right, so I think that's 16, yes. So let's go back to the opcode decoding. So it starts with 110. Where's the opcode encoding table? Okay, so 110, but which one? 1101, right? Conditional branch and supervisor call. Okay, so 1101, and then we have like 110, permanently undefined, huh? Undefined instruction exception. Interesting. So maybe that's the way it sets breakpoints. Oh, wow. Wow. Okay. And this one. Okay, interesting. Undefined. The operation is undefined. So it does throw an undefined instruction exception, but do we actually, did we? We didn't capture the output, but let's do this again. I'm wondering if we got an interesting, like this instruction somewhere in the output. The output is actually not that long. Interestingly, reading memory from invalid address. Why is that? It's reading from an invalid address. Okay. Okay, yeah, we got one instruction that wasn't implemented yet. What was this instruction? Maybe we decided not to implement it in the past. Yeah, that's something that we had before. So it's not relating to the GDP. So I have no idea what's going on here. Like, why it is. Yeah, this is not useful without the debug info. But yeah, why GDB isn't doing the breakpoints the way we guess it would do. Let's just make sure that the memory writes work before we blame GDB. So we had this write memory. Okay, interesting. So we didn't use the lengths. We can probably deduce it from the actual lengths of the data, but just for the good measures, we can do lengths in bytes. So we can cut a string to lengths. And then let's write to, yeah, we haven't tested that code. It could be that we have some bug that writes garbage to the memory, don't know, to plus I to string 16. Okay, cool. And then let's try that again with GDB. And we know that even a step should generate write instruction. And we get a lot of garbage. Yeah, maybe let's do this and send the output to a file, so we don't get confused with all the output. Okay, stepi, and then we can see here reading. Okay, we are reading all this stuff, but we need to have a write. So yeah, it seems like it does the right thing, like writing those values to this address, but I have no idea what these instructions that it's writing here are. Definitely. So what we're going to do, I wonder if I try to disassemble something. That was 10,000, right? No, we need one more zero. Is it like, yeah, I think it's reading it from, we didn't to string 16 it, the address here. But anyway, when I disassemble, you see it's sending a command and it's reading the data from the memory. So what I can probably do, is there a way I can send it? Probably there isn't an easy way, but I can try to do something like, where was that M command? Uppercase M. I can probably try to manually write this data to the memory, and then verify that I can read it back. So in GDB that would be set probably uint 32t equals, and then this is probably yeah, I would need to convert it to change it to be big Indian, little Indian. So E7 F001 F0. Ooh, he didn't like that. Yeah, maybe I need to cast it into a pointer. Okay, let's see if it sent the same command. Huh? Is that what it sent now? It seems like the same command, but I'm not sure if it sent that now, because it sent a lot of bunch after that. But let's just, try to disassemble, or maybe just try to print it first and see what happens. Yeah, as hexadecimal. No, it doesn't seem to have written it. But anyway, so we are in line 815, and then let's see what happens if we do this set. So yeah, so we can see it sent the same command, and we were supposed to write these values, but if we read them back, we get different values. So I guess we haven't implemented writing to the flash. Let's see, what does writeUint8 do? It reads and then it calls this one. And yep, we haven't implemented writing to the flash, and that's why we can't GDB can't write there, and it doesn't fail in any way. Like we don't yeah, we don't report this as an error. We just maybe we should console.error write to undefined address and address to string 16. That would have saved us some time now if we had a debug log. And then we can also implement the writing to the flash, and we can also do it with the bootrom. So this would allow us to set breakpoint inside the bootrom as well. All right, cool. So instead of get, it should just be set, and we set it to value. And for writing to the bootrom, we just cool. So I think that should do the trick. Now we can write to the flash and to the bootrom. And I wonder why the process didn't restart. Anyways, let's restart GDB. I will just copy this command so we have it. Took us some time to figure it out. Okay, let's reconnect. Huh? Okay. Yeah, now we can see a lot of invalid memory address reads. I don't know why we have that, but probably GDB doing something strange, fancy. I don't know what was going on there. Yeah, it was trying to read from those addresses for some reason. I don't know why. Anyway, yeah, we wanted, okay, let's be super optimistic and see if stepping just magically works, and I think it doesn't, because it does all sort of strange reads. But yeah, I think we got into some very bad situation here. So probably the write have worked, but yeah, it probably wrote some garbage there, and it messed up with the code in some very strange way. So let's retry that, and let's try this and see if that sends the. I mean, we already know it writes to the memory the same way. All right, we did this right. We can see it here, and now let's try to disassemble this. Okay, so yeah, I think I think that's the 2 bytes that GDB has put instead of what we had before. Let's copy it and see what we had before. We don't know why GDB does that. Maybe that's a bug with GDB. It doesn't put the correct instruction because, oh, maybe we need to tell it somehow that we are in thumb mode. So maybe this is like the break instruction. Yeah, I think that's the problem, and that's why it also puts it like 4 bytes away and not 2 bytes away. So it probably doesn't realize print $PC. Yeah, I get it. So in ARM, the least significant bit of the PC register says whether we are running in thumb mode or in normal ARM mode, where each instruction is 4 bytes. And since at the beginning we said the PC and the LSB is clear, then GDB assumes that we are running in standard ARM mode and not thumb mode, and then it assumes that the next instruction is 4 bytes away, not 2 bytes away, and it puts it sets here the opcode of the breakpoint instruction for the standard ARM, and this is basically nonsense loop in which goes to negative offsets in this thumb mode. So that's the problem, and we'll fix that in a moment just by setting the LSB of PC to 1. But before that, Che Guevara said we had copy for flash write copy paste bag. So let's take a look at that. I mean, it worked, but maybe we did have some bug. I don't see here anything that jumps to my eyes. So Che Guevara, if you see something, just let me know exactly what it is so we can address this. This looks legit to me. Yep. Anyways, so all we need to do in order to fix that is just, to initialize the PC to this value. So the least significant bit is set, and until now it didn't matter because our emulator doesn't care about that, but now when GDB connects, it starts being important. So we restarted the code, and now let's restart GDB, and let's see if stepping works. Oh, I shouldn't type quit here. Okay. I wonder why we have those errors here. I don't think they were before. We done anything wrong? Maybe that's the line 200. Maybe that's what Che Guevara was talking about. So what is? Oh yeah, we shouldn't have the return error, but I don't think it matters. Is that what he meant? Because I don't think it really matters that we had a return. In any case, we wouldn't do anything else, and it's okay to return in JavaScript a function that returns nothing. It just returns undefined. So thanks for spotting that, but if that was the problem, then it's not a big deal. Anyway, let's go back to GDB and let's see if we can step now. Ooh, what happened? I think it restarted because we changed the code. So let's restart it and stepi. No, it's still doing weird things. Okay. Yeah, I'm setting a new value. I'm calling setuInt as far as I can tell. I changed it, but I still had a return. So I think that was the thing that was confusing about it. Anyway, let's see what GDB does now. When we do stepping, if it still writes this nonsense. So yeah, we can now see that the LSB of PC is set, which is good. And then set debug remote 1 and stepi. And yeah, I mean, it still does this nonsense. So that hasn't really helped. Unfortunately, GDB doesn't want to, even though we have set the PC correctly, it seems like GDB doesn't want to send the correct opcode for breakpoint. So let's Google this real quick and see if there is a solution. GDB arm thumb bkpt. Set arm force mode. Okay, let's try that. I mean, it's not optimal, but if it works, let's just restart the process. If it works, then it's fine for us for now. All right. Why is it dead? Okay. Thumb. Okay. No, still no, 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 just no. Get arm force mode. Help set arm force mode. But what modes are available? I mean, it's disassembling it correctly, but it's not doing the correct opcode. Wow, this person is having a lot of trouble with getting GDB to work. Let's see what happens if we just put here some garbage. No, so thumb is probably a, oh, we set it, the fallback. What's the fallback mode? Oh, okay. So probably, oh, there is a bug in GDB about that. Interesting. And yeah, I can't really view that. Link to the wrong URL. Yeah, well, okay, let's try a different approach. Instead of like doing it with like GDB setting breakpoints with the bkpt opcode, let's try to implement the Z instruction. So let's just let GDB set breakpoints, and we'll take care of doing the right thing. So there was like this Z command. So it sends Z0, I think. Where was that? The output. Yeah, Z0, and then but it sets the breakpoint in the wrong address anyway, so that's pretty annoying. I mean, we won't be able to step correctly even if we do this. What is for? Kind. Other kind. What is kind? Yeah. Is implemented. Target specific. The size of breakpoint. Yeah. So probably GDB assumes that we have like for some reason GDB assumes that this code is what if we try something different and we force the mode even before we load the executable thumb. Not thumb, thumb. Okay. Oh, and we probably need to run the process. Yeah, so GDB can connect to it. Okay. Yeah, it's still doing this weird thing with the reading from these weird memory addresses. I don't know why it tries to read from those addresses though. Oh, whoa. Oh, well. Maybe it's because, oh, I have an idea why it's trying to read from those addresses. It's probably because the registers aren't initialized yet and it's looking to read data from the stack, which is initialized to 0. So I think we had a code to initialize the stack, but I'm not sure. In execute, where's that run link? Did we have a code to initialize the stack, or does the, yeah, probably it happens somehow in the simulated code, or maybe not, I don't remember. Yeah, we initialized the PC, but where do we set the stack pointer? In the constructor, we read it from the bootrom. Yeah, the stack pointer is initialized, so I have no idea. It's probably trying to read the from the stack the frame history or something, and that sets it off to an invalid address since there is nothing in the stack. I have no idea. Anyway, let's try to step and see if it still doesn't work, which is probably the case. Yeah. Where was that? GDB, reading. And then it's writing again 4 bytes, or it tries to set a breakpoint in the wrong location. Yeah, that's not nice of GDB. So maybe we are just a bit unlucky with this function, because I think we have seen that in other places it worked well. So maybe we're just wasting the time here, and we can try to do something else, which is just what we tried before, where we had that break here, and we know it should get there. Now let's continue and see what's going on. Okay, so yeah, it didn't break where we wanted, but let's see what it tried to do. So yeah, so in this case, it seemed like it wrote this value, and that's the correct address and 2 bytes, and it also uses those Z instructions and X instructions, and like it tries to set a breakpoint, it failed, and then it tries to write this value. Let's see what this does. So let's use GDB again to manually write here and disassemble this. Don't need that at the moment. So, and we want to write DE01, and that's UN16 in this case. And before that, let's see what we have at the moment at this location. So let's disassemble it. Yeah, so right now, this is basically the address, the beginning of this function where we wanted to set a breakpoint. It has a push instruction. And let's see what happens after we do this set. It should have a different instruction now. Yeah, UDF. So it seems like GDB uses UDF for its breakpoints, which is interesting, but we can deal with that as well. Let's see what happens when we do a step. So when we send a step, what does it send? So here we go again. I think it does the same thing, annoying thing again, writing 4 bytes. And at this point, I think it would be a waste of time to keep fighting with GDB. So what I'm going to try to do, I'm going to see if it works differently with the actual Raspberry Pi. So I still have that setup from last week with the Raspberry Pi connected through OpenOCD. So it's here waiting for connections. So you can see I already connected to it before just to test the setup. So I'm going to restart GDB and now connect to the Raspberry Pi at that same port. We're open. Let's remove that force mode. Oh, and yeah, we are actually running Blink on the Raspberry Pi. So let's load the correct ELF file. Actually, yeah. So it's blink.elf. I think that's the correct one. Yes. Okay, that's not a Raspberry Pi, it's Raspberry Pi. Okay, cool. So we are in we are somewhere in the code. This is on the physical Pi, not the simulator. And let's step one instruction and see what happens. So first of all, we can see that it worked, I think. Not sure. We stopped somewhere. But let's see what it sent. So okay, it sent this command and then it received this response. So it says verbose resume is supported. Oh, it sent a stepping command. Interesting. So maybe we should support this vCont thing. So GDB would be able to send us step commands instead of like doing it the wrong way. So maybe that's the way to go. So when we get vCont ? We should answer with this. Let's do that. Okay. By the way, you can see here that GDB is also doing like reading from invalid memory locations. Yeah, EORS is saying is having doubts about those reads from invalid memory. So yeah, I can definitely run the code without GDB, or even I can do what we had before, which is just, I think we had like a loop here. Did I comment it out or something? That would just run the same code. We have the Git history. But first of all, before I, let's paste this thing here before I lose it. There was some, yeah, there was this loop that would run the code before calling GDB. So let's do that. Just to clear the doubts of EORS. So running now, and it should execute like 20,000 instructions. And yeah, you can see it got into, we got a lot of breakpoint output. Let's reduce the number to 10,000 just so we have less output. But yeah, we consider still like a few reads from invalid memory address, even though we run it without GDB. So I'm not sure. There is also one write to an undefined address, or a few of them, which we haven't seen before because we just ignore them. But that's probably some peripherals we are reading and writing from. We can take a look in a few minutes what's there. Anyways, okay, so yeah, let's remove this and implement this vCont instruction, so or command. So basically GDB sends us vCont ? Oh, but did I save the response? Yes, and we should answer that with this. So and then to step it just sends vCont semicolon stamp S1. Okay, so if it starts with V, maybe we should also take a quick look at the documentation. If params, oh no, if cmd equals vCont turn GDB response, yep, and then how does it work if we don't have anything? Yeah, maybe we should remove this return here so we have a fallback. Okay, so then if cmd starts with, let's quickly take a look at how this vCont work. So vCont semicolon action and optional colon thread ID, and C is continue, and S is step, and T is stop. Okay, so let's try it. So if it starts with C, or actually that was vCont C, then we just continue. And if it's just S, that's what it sends to the Raspberry Pi. vCont semicolon S, yep, S, and so it probably tells it's to S and then thread number 1. So step thread number 1 and then continue probably with the other threads. So stepping just the current thread, and we don't have multiple processors, so we don't have to worry about that right now. So if it asks to step, then we just step. So step means executing just running one instruction. Okay, and then reply the stop reply packet. So what happens here? So yeah, T05, and so after this packet it executes the instruction, and then it replies with one of those packets, and it says T05. We sent S05, and the only difference is this is the equivalent of S, but it has also other information, so it doesn't have to query us about the registers and thread and whatever. But yeah, I think this one will work as well. Let's try that. So basically we should send here this response as well, which means maybe we should extract this into a constant. So this is called stop reply. So let's call it stop reply trap S05. So we said 05 is like a trap signal or breakpoint signal, and we have it already appearing 3 times whenever we have a breakpoint, or now when we are stepping, and also when we are starting. Okay, so let's give it a go. Let's try that. Quit. We have that one which connects to localhost, but without the force thumb mode. Okay. All right. So, are you ready for the moment of truth? We are going to stepi and see what happens. And okay. Yeah, a lot of invalid memory reads. It seems like it didn't really step one instruction. It seems like it got into a loop or something. Okay, let's see what it sends. Yeah, so it should send us vCont S, and then we should execute one instruction. But let's see what happens. What really happens? Set remote debug 1. No, set debug remote 1, and we can stepi. Okay, interesting. So what happened here? Ooh, it didn't even try this vCont thing. Oh, it did try it, but it didn't try stepping for some reason. It just it tried to do the breakpoint thing, and then it used vCont to continue. But so it behaves differently, and I guess the reason might be that we are sending something incorrect in the initial query packet. So we had that supported, and we only say that we support packet size. Maybe we should look at what Raspberry Pi says. So EX just tells GDB to execute a command before when it starts, so we don't have to type the commands every time. Okay, and now we can see that's GDB chatting with the Raspberry Pi, and we can see that it says it supports multiprocess, software break, hardware break, fork, exec. Okay, vCont supported plus sounds like a good thing. Thread events, no resumed, XML registers. Oh, that's what we are sending. That's what we are replying. So we are saying the Raspberry Pi replies, it supports this, red plus, XFAIR features, red plus, threads. Oh, this is like, so it supports this, and this. Yeah, I guess we should also indicate that, let's copy that line just so we have it as a reference. But I guess we should also say, tell GDB that we support now vCont, and that might be useful in letting GDB use that command to step. I don't know. Let's try that. Okay, and now we can connect to our GDB, and it's reading the symbols, it's connecting, a lot of invalid and stepi, and oh yeah, it worked. We managed to step, and now we can do this. Finally, hooray. So it was this vCont that we needed to implement, and now we can step, and you can see we can go one instruction at a time. Isn't that amazing? And see like the result, like what was loaded into R0, in this case -1. And yeah, there is like a bunch of invalid memory address reads, but I don't care about that because I'm super happy, because finally we got stepping to work. And then I think the next thing would be to see how we can get breakpoints to work, and then we have like the full power of debugging once we have proper breakpoints. So let's do something really simple. Let's try to set a breakpoint at like this address, which is just a few instructions below. No, layout CMD, no, focus CMD. Okay, so now breakpointing at this. And you can see here there's like an indication that we sent a breakpoint, and let's disable the TY, this mode, because otherwise it will be hard to see the instruction history. Set remote debug 1, set debug remote 1, and continue, and let's see if it stops. So interestingly, it did set like so we already know that this memory write means that it's that UDF instruction. So I guess what we are going to do now is just to see how it works with the Raspberry Pi. So eventually the setup I said last week now proves really useful, because we can see how things are working on the Raspberry Pi 0. and just make not the emulator, not the emulate the CPU that it works the same as the real hardware, but the debugger actually. So let's see where we are. This PC, this ASPC. So that's another way to see where we are, but I actually prefer the layout assembly, this one. So we can breakpoint at PC plus 8. No, break maybe this way. Yep. So we have this breakpoint a few instructions away. Actually, no, that's not a good idea because we have a branch one instruction before that. So let's set another one, PC plus 6. So we'll surely hit that very soon. Oh, we actually have, let's just step one instruction so we know. Continue. Yep. So yeah. So now we are here and we have a breakpoint 2 instructions away, and there is no branch in the middle, so we know we'll eventually get there. And now we have 2 breakpoints. So let's delete the first one. It's removed when we have only 1 breakpoint, and let's disable the text UI. TUI disable. Cool. And now let's just continue and see how it sets the breakpoint here. So yeah, we can see this is the breakpoint. So before the breakpoint we have continuing. Oh, I see. It just uses those hardware breakpoint for that. So in this case it doesn't even use the software breakpoint. So basically now it's up to us if we want to whether we want to implement those hardware breakpoints or doing with the UDF instruction. I wonder why. Is there like invalid instruction? What undefined instruction exception? But how does GDB hard fault? How does GDB trap that? Yeah, I think I assume GDB would. Maybe we can tell GDB set breakpoint with bkpt arm. But there is a bkpt. Interesting. So on ARM Linux it's and bkpt in TAM, but for some reason it still uses undefined opcode. Yeah. So yeah, let's try that. Let's try to implement that and opcode, and if we have this and opcode, just act as if we got a breakpoint, and I think that should be good enough for now. Yeah. So that's and opcode. Where are you? Core. Okay. So breakpoint. Oh, there is a breakpoint unit. Interesting. Anyway, not something we should worry about right now. So yeah, that was instruction details and UDF. So basically let's add it. Another new instruction, UDF, the undefined instruction. Okay, so let's go to the end of this humongous file. Okay, it fits here, UDF, else if opcode. So that was the prefix, and then we have const im8 equals opcode ff, and just do as if it was breakpoint. And let's real quick do add a test case for that. Do we have like the opcode for that? I think maybe in output UDF, that was where it wrote. Yeah, we had a opcode, but we can easily regenerate it. Okay, so let's reconnect GDB to our code. All right, and then let's just set a breakpoint in that function. Doesn't really matter. We just want to see. Oh, actually, we have it here, right? 1DE. So yeah, so let's do the test case. So where is the RP spec TS? So you str SXTB UXTB. Okay. So let's do I think that was UDF01, but we'll take a look in a moment. UDF01. Or just UDF1. We don't need a 0 here. It's confusing. All right, so rp2040 dot on break is break mock, and we'll define a mock const break mock. So that's just something that the testing break framework gives us. Just .fn, yeah. So basically, it's a function, and then we can a callback that the testing framework just defines for us, and then we can just assert on that. So we can assert that expect this mock to have been called with 1. So yeah, it doesn't pass because the PC hasn't been updated. Oh yeah, right. We need to change this. Huh? Oh, to have been called with 1. Okay, so it wasn't called. Let's see why. Maybe the opcode is incorrect. Yeah, I guess. Yeah. I think it was 1DE or DE01. Yeah, it's DE01 according to the opcode, but why doesn't it get into the if statement? By the way, Che Guevara's suggested that we tell GDB that we support software breakpoint, and I think if that won't work, we will do that, because we already have, like, managing breakpoints. It's a bit of a pain. We have to keep track of them and then compare them in the execute function. So I want to try to avoid that, but if we can't, then if that doesn't eventually work, then we are probably going to give up. And what's the encoding for that? And try to go that route of implementing the breakpoints ourselves. So yeah, DE01. So why doesn't it match here? Why are you What happens here? Why don't we get into that if statement? Maybe it's matched by another instruction. That was this dot upcode to string 16 and DE01. So without it to string. One one zero one 1111 1101 111. Wait a second. This is the same, so why don't we get into that if statement? What did I miss here? Oh, interesting. So branch also matches this for some interesting reason. So do we have a bug with branch decoding? B 1101. Huh? Interesting. 1101. So how comes undefined use the same prefix, right? Maybe, oh, maybe there is like a single condition. Yeah. All right. Yeah. So can't this value, like these two values are like used by other instructions. So basically that's a problem. So this is good that we added this test case. Otherwise we wouldn't have figured that out, and we would have to like bang our head against the wall why this is like not executing. All right, so we can just say and so if this basically if the next 3 bits are they shouldn't be 111. So if code shifted by 9 and 7 isn't equal to 0B111. So maybe now no, the parentheses got messed up. Okay, so maybe now, yeah, green passes, perfect. So yeah, now we fix the decoding of branch, not to interfere with the decoding of UDF1. And yeah, I think we are good to go. Let's see if we can set breakpoints correctly. I mean, we know we can set them, but they weren't firing. So now let's see if the breakpoints are firing. So hey Guido, welcome. So I see that you joined the stream. We're in the middle of trying to we got GDB to be able to connect to our program and inspect the current state, but now we are trying to implement breakpoints and stepping. So we already got step to work, so we can step and it will execute the next instruction one at a time. And that's so much fun. We can go over the code instruction by instruction. And now let's switch to assembly and let's be super optimistic and set a breakpoint like 2 instructions apart. So we have this breakpoint and I'm going to continue and let's see if it magically works. Oh my god, it worked. There is only 1 point. You can see that we stopped in the incorrect we stopped in the incorrect place, and I think the reason for that is when we have a breakpoint, we should not change the PC but here we already incremented PC by 2. So for that, we would need to fix our breakpoint. Where are you, breakpoint? Yep. So that's in the GDB server. So where is the breakpoint handler? GDB breakpoint on break. Let's close that. We don't need that anymore. So we can say .pc goes minus equal 2. So it goes to where we set a break instruction. It doesn't continue. And now I don't need to restart it. It automatically restarts. Okay, now let's try that. Let's be super optimistic and just breakpoint here and continue and see what happens. All right, yes, we got breakpoint working. You see, it broke. We got the breakpoint, and we are where we were supposed to be, where we are in this function, and we can see like the parameters probably. If we this is like 3, alarm none 3, callback. This is the callback. This is so useful. We can now like step like let's see if that works. Let's go layout source and let's try to run the code line by line. So I write next, and yeah, it wasn't exactly line by line, but we did stop a few lines after, and let's see if we can print the variables. So yeah, we can see that arqnum equals 3 lock, and we can see the value of lock, and it's where did it go? Not sure. Anyway, we can print star lock, and we can see like the value of lock. If it was a struct, we could have probably, yeah, it's -1. And then I can like next, and maybe it will take me to the next line. I don't know. I think when we do next, yeah, GDB just set a breakpoint, a temporary breakpoint for us in the next line. So, and then we can print the value of save, and we can see it's 0. So yeah, basically we have the debugger, and that's super. I'm super happy about it. This means we can now start debugging and understanding what goes wrong with the code in the simulator. So one more thing that I want to do before we can declare our work here as finished, because we have what we need to debug. We can set breakpoints, we can inspect values, we can modify memory values, we can basically, thanks Jem for the nice emojis in the chat, we can basically debug the code now with GDB, even though it's running in the emulator, and we no longer have to resort to use those ugly trace files, which is, wow, great. They will probably still be useful in a way, because we can see if we want to check why a specific place in the memory was written, or check if there was some error, that would be useful. But there's one more thing that I want to do before we sign off. So if I just continue, oh, nice. So we also now received like it stops when it gets to that failed assertion. I think we had that before, yeah, or but now it stops in the correct line, so we can see that yeah, we just stopped here with this failed assertion. But yeah, so let's commit that. I think that's a good progress. Let's just first of all, we added UDF instruction and bkpt, but basically we implemented a bunch of new features to support this scenario of debugging code with GDB. So this is good, and then we had this GDB service changes. So first of all, feed RP2040, implement UDF instruction also add execute and stop methods that are used by GDB. Cool. Let's just take another quick look before committing. That looks legit. And private stopped, debugging. We have a to do here. We'll do it one day, maybe. And then we added, okay. And implement writing into the flash bootrom region so that GDB can set breakpoints there. Cool. So we also did that. And then fix the decoding of the branch instruction. Cool. Okay, so one more commit for today, and then now we can commit the changes in the GDB server. Let's just go over them really quick to see if we haven't had any. Yeah, we removed that, so we now already we always stop at the beginning of the program instead of like stopping after executing 20,000 instructions. So we can set breakpoints and do things. And we have vQuery, continue, G read registers, M read memory, write memory, and the break callback, which worked, happily worked. Yeah, I think that we are good to go, probably. Implement stepping, breakpoints, and memory writes. We don't need implement. Fit means that we added a new feature. So stepping, breakpoints, memory writes. Yeah, that's the features that we added to GDB server. Okay, cool. So wow, 3 commits already. That was a lot. So now I think we have sort of 20 more minutes. So I think we'll use that time to figure out what goes wrong with the Pico, why it goes crazy. Actually, I'm thinking maybe maybe we can try something else. So no, we'll do that. I wanted to see if we can set up Visual Studio Code to use GDB. So we will be able to use the user interface of Visual Studio Code, but I think that's good enough for now. Like the GDB, it's a good opportunity for people watching this stream to learn how to use GDB without like fancy GUI, and it's very powerful without a fancy GUI. Anyway, let's restart, and now we have a setup that is working. Oh, we need to restart. Okay, actually there is a nice trick we can do. So we have like this situation right now where the program stopped at this breakpoint, but I think we can do something like that to just run it from the beginning. Let's see if that works. Oh, I think we haven't implemented writing into the registers, right? So let's see. Print R0, set R0 5. Yeah, I guess we haven't implemented writing into registers, just reading from them. There is like another command that we should probably implement if we want the full debugging capabilities, such as updating the value of registers as we debug. So there is like this command list, registers. So there is G read general registers, and uppercase G is write general registers. And basically it's the same packet as in the read register. So just the values of the registers, and then we say okay. So let's quickly implement that. GDB server. So case uppercase G is write registers, and then yeah, we are just doing the opposite. So we have this method in decode hex buff that can convert. Okay, so we had this method that could convert like the parameters of the command. Let's see how GDB sends it. All right, there is an easier way to do it. Set debug remote 1. Yeah, so oh, it does send a P packet to set registers, not the G packet. Interesting. Okay, so what's the P packet? Read, oh, there is like write register N with the value R, N hexadecimal, R 2 hex digits, target byte order. So in this case, we are setting R0 to 5, so it's setting R0 to 5, and that's like in a little Indian. All right, so let's do that. Let's implement P. Let's see what it sends when we set PC though. When we set PC to, let's say, this address. Yeah, again with P, and then value name equals value. So yeah, so yeah, we don't need G, we need P. Okay, where were we? GDB server. So instead of G, let's call it P, and that's write a single register. And then just like with write, let's split it at the equal sign, and then const register index is, what's the reply to P? Okay, for success, E for an error. So params F0 yeah, base 16, and then const register value. And now that's like it's pretty annoying because this is like we are getting it as a little Indian value. So we can do this trick, uint8 array encode decode hex buff params 1, and then cast it to a 32-bit array to read it as a 32-bit integer. But first of all, let's do a couple of checks. If register index is less than 0 or it's more than 16, 15, yeah, then we just return an error. GDB response is 00, I think. Yeah, don't know what 00 means, but it shouldn't happen anyway. Okay, or params1.length, let's give it a name, const register value is params.1. So if the register value length is not exactly 8, because it should be like 8 hexadecimal digits, we return 00. All right, and then otherwise we just decode this register value. Oh, well, let's just call it value then. Value buffer, and we can take the buffer out of that, and then we can say rp2040.registers at register index equals new uint32 array value buffer, or we can do it with data view. Oh, too many ways to do the same. Dot get uint32 at offset fs, and it's Little Indian. Yeah, so much code to just do this conversion. Anyway, and then we can say just GDB response. Okay, so at this point we should be able to write to our register as well. Let's try that. Yeah, R0 is now 0, set R0 equals 15. Oh, why didn't it work? Let's just print those values. Probably I'm doing something wrong there. Yeah, now I need to reconnect, target remote Windows 333. And then I can set R. So, looks legit. Not sure why it like this one shouldn't be a problem. So the length should be 8, probably. Maybe perhaps we have some kind of space or anything before or after that. Maybe we can just trim it for the good measures and see if that helps. Remote debugging. No, still not happy. Okay, let's just try to print each of those conditions to figure out which one fails, and then we can further look into this. False, false, true. Oh yeah, right. This should be not equal. If it's not equal 8, then we should fail with an error. That makes sense. Okay, let's try that again. Reconnect, and then setting it to 15. Print R0, 15, info registers. Yeah, it seems good. So we have, let's try this layout assembly, and then let's try to just jump to some random place. Let's see, $PC equals $PC plus 8. And yeah, it works. So now we can just jump randomly in the code if we want to. Cool. Yeah, so let's another commit. Fit GDB server set register command. Actually, let's just that's set register write register. That's how they call it. Write register. Okay, cool. Yes, another nice feature in the GDB server. Okay, so now we got about 10 minutes to play with GDB. So I think at that point I would probably keep the part of like actually playing with GDB to the next episode, next week, the 10th episode. But I think we can try in these 10 minutes to get GDB to work with Visual Studio Code. So let's see if I can, if I'm able to set this up. It shouldn't be too complex, just figuring out the configuration. So start debugging, and then that's C++ GDB, and then so many configurations. I think ARM non-EABI GCC sounds like a good There isn't a multi-arch. Okay, let's try that. And now I should have a new configure task. Okay, so now I have this like configuration file where I can tell it which GDB probably to use and stuff like that. And there is a way to tell it which file I want to debug. So in this case, I want to debug hello UART, which is we can just give it the full path to the hex file. And let's call this configuration debug hello UART. Okay, and stop at entry. And how? Oh, yeah. Now I can tell it which GDB to use. Which GDB multi-arch. I want to use this GDB. Not this one, this one. Okay, let's see if this works now. I want to run this. Did I save that? Where did I save that config? Inside Pico examples? I have the config, so start debugging. Okay, so I started debugging. Couldn't find the task, C++ active file. How do I choose? Maybe I go to the debugging. Oh, yeah. Maybe if I play here, that would work. Something isn't. No, I don't want that. So there we go. We have this configuration. But why doesn't it? Oh, I think it's trying to run another task. First of all, the program is not correct. Maybe the request is not lunch. Yeah, maybe I don't need this pre-lunch task. That's what's driving it crazy. Okay, so maybe I do need the extension. Let's try now. Yeah, it's allow UART / allow UART. See if this is the correct. I have literally no idea what I'm doing, but it seemed to have set up some GDB, but you see it's running GDB, but there is a problem. Unexpected, can't insert breakpoint. Oh well, we also need to tell GDB to connect to the simulator. So let's see how to do that. Out GDB VS Code. There is a target parameter and a remote probably, or there isn't. Type GDB. Oh, oh yeah, this looks so I need this one probably. Debugger address. So I'm going to connect to WinHost at port 333. Let's see if that works. Again, I have no idea what I'm doing, but it seems like we got into GDB, or maybe not. What happens here? Yeah, cool. So now I can also use Visual Studio Code. You can see like it's connected to GDB, and I can see the stack trace and go away and like look at all the files from this very convenient interface, which is pretty cool. And let's try to go to the beginning. So let's try exec set pc equals this. Attempt to assign to an unmodifiable value. Interesting. Yeah, interesting. I'm pretty sure there is also a jump command that may help us. Jump to here. Interesting. Yeah, it's trying to write to the register XPSR, which we haven't implemented. It was a to-do, so interesting, but I think we are in the correct place now, right? Info registers. Where is PC? No, we didn't go there. Anyway, what we can try to do is just to restart the whole thing. And then run GDB again. And where we are right now, stick trap. Yeah, flash binary start. So let's try to see if we can. No, it seems like whenever Visual Studio Code connects, it already runs the program. So let's try to do something like that. Let's try to restart it again and set a breakpoint here in Visual Studio Code and see if that would work. So restarting and connecting, and now it's starting GDB. And what happens? Yep, we got into the breakpoint. So yeah, so now we can also like do this even more fancy debugging, where we can use this user interface instead of the text user interface. So we don't actually need this GDB console for now. It's not very fast though. We can probably fix that by removing all those debug prints of the protocol that slow us down. But we can do that next time. Oh, we can do that now. It's easy to remove them. So don't be lazy, Ori. So that was just setting debug to false, I guess. That was simple. And let's restart the session. And we already have the breakpoint, so it should stop here as well. All right, yeah. Now I hope it will be a bit faster. Still a bit slow. We don't have all those, probably those reads are slowing us down. I don't know. Anyway, yeah, and we can now like see that how the code is running in the simulator, in the emulator. Yeah, we should definitely try to make it somehow faster, but other than like this interesting slowness, it's pretty cool that we can. I think one thing that happens, I'm not sure about this, but no, I think when we do, yeah, we now hit that breakpoint, that this function, like we should have stepped into it and see what happens there. But yeah, so now we have like a super convenient way to debug the code with this configuration in Visual Studio Code. So it took us like 10 minutes or so to come up with a configuration that allows us to hook Visual Studio Code into GDB that connects to our emulator and can debug the code, which is wow. I'm absolutely happy about this setup, and next time we'll use that to finally debug that weird issue. Where is that issue? Weird issue where we just get this exception because of yeah, this is probably something here, like this is the thing that fails at the breakpoint here. It already failed, but yeah, anyway, we can see that yeah, probably failed. Can we see the assertion that failed? I don't know, but yeah, it's probably this one, if this is like where the breakpoint, or maybe so one annoying thing about stack traces is that sometimes, yeah, this is assert and it probably resolves to assert func or God knows what. Sometimes because of like compiler optimizations, you don't really see like the entire stack trace. So it could have been here, or yeah, some functions like are just removed from the stack trace or inlined. But anyway, I guess once we like next week, we'll probably set a breakpoint here. We'll look at this, and probably I think we already concluded like last session that this is the assertion that failed, and we looked into this table and like into this function, and we didn't have all these fancy easy ways to see what's going on with the code. So next time it will probably be faster. Anyway, so yeah, that's it for this week, and thank you for joining me. This time I'm pretty happy about the setup. If any of you wants to try to replicate the setup, like you need to install this GDB multi-arch, and if you want to try to debug it this week and figure it out before the next session, and then open an issue on GitHub and tell me, hey, this is what's going on, this is what's wrong, then that would be cool. And if not, then that's also totally fine. We'll just do it next week. I think that's going to be very interesting to start finding all those points where the emulator fails because of unimplemented peripherals, and we also got the physical hardware, so we can use the same GDB setup to debug the physical hardware and compare how they the behavior. So now we have like this setup and tools that would allow us, like open a lot of possibilities of how to approach debugging this. So yeah, I'm already looking forward for the next week, and thanks for all the comments and the interaction in the chat, especially Che Guevara's, which was really active today. And see you next Tuesday. Bye bye, and have a great week.